Okay, section 12.8, exponential and logarithm problem solving. So we have two things to do in this section. Number one is to solve a bunch of equations, and then do some problem solving. Now the primary focus is going to be on solving equations, not problem equations, problem solving. So our primary focus is going to be on solving equations, and the reason for that is problem solving. We're going to do one or two examples of a word problem, but essentially it's about understanding what type of equation you have, exponential or logarithm, making sure your variables are identified correctly, and then solving it. So that's all stuff that we've been doing all semester. We've been looking at word problems, we've been extracting the information out of them, making sure that we have the right labels for the right properties, the right labels for the right variables, so on and so forth. So we really want to dive in deep on solving logarithms and exponentials, and these come hand in hand because, as we've outlined in the last few 5 sections, they're the same thing, or I should say they're equivalent. So we're going to solve just a bunch of equations. So our first one, 3 to the x equals 7. So this one's a little bit simple, but when you're solving an exponential like this, what we want to do is use properties of logarithms. So we can take log base 3 of 3 to the x equals log base 3 of 7. So notice we've taken both sides of our equation and applied the log base with the base that we see, because we know log base 3 to 3 to the x. This, according to our properties, just becomes x. And this equals log base 3 of 7. Now this isn't the only way to do this. We could also have done log 3 to the x equals log 7, using the common log that we just discussed in the last section. And then our logarithm properties kick in, the x comes down, we have x log 3 equals log 7, or x equals log 7 over log 3. Now, these are equivalent, again, from the last section, using change of base. So log base 3 of 7 can be switched to the common base by doing log base 10 of 7 over log base 10 of 3. So it doesn't matter what logarithm you choose, the base that you have, the common base, or as we saw at the end of the last section, we could also have done the natural log. Either way, these two answers are equivalent and both equally acceptable. It just comes down to how you feel and what you want to do to tackle each problem. So let's look at another equation. Let's start with logs this time. So let's have log base 2 of x plus log base 2 of x plus 1 equals 1. So the first thing we do in this, for this one, is use properties of logarithms. Since we have an addition of logs of the same base, we multiply x times x plus 1, and that equals 1. And then now what we do is we raise 2 and 2. So this is 2 to the log of all of this, and this is 2 to the first. 2 to the log base 2 cancels itself, and we get x times x plus 1 equals 2. Or x squared plus x minus 2 equals 0. And now we're just solving this quadratic. This is going to be x minus 2 times x plus 1 equals 0. Bringing that over here. Oh no, this needs to be plus 2 and minus 1. So plus 2 minus 1 gives us x equals negative 2 and x equals 1. Now because these are logarithms, we have to make sure that we're satisfying the domain, and we know the domains of any logarithm starts at 0. So negative 2 can't go into here, so we're going to cross that out, and x equals 1 becomes our final answer. And that's because our domain doesn't allow for negatives in the argument. And since this is just log base 2 of x, we have to make sure there's no negatives there. So let's try a couple more. So these next few, I suggest that you pause the video after I write them out and you have them written down so that you can try them on your own. So the next one will be log base 7 of x minus 1 equals 2 log base 7 of x. So basically what we want to be doing each time is using properties of logarithms or properties of exponents to rewrite these in a more fortuitous version, something that we can actually solve. So try pausing, manipulate these using our properties of logarithms to try and solve. I'm going to start going through it now. So I can move this over and have log base 7 of x minus 1 minus 2 log base 7 of x equals 0. Now if I want to combine these two logarithms, I need to make sure that the exponent here is actually an exponent and bring it back up to the top. So we have log base 7 x minus 1 minus log base 7 of x squared equals 0. Now we have a minus and the same base logarithms, so we can write this as log base 7 of x minus 1 over x squared equals 0. Raise 7 to that logarithm, 7 to that side, each side of our equation. 7 to log base 7 cancels itself. We have x minus 1 over x squared equals 7 to the 0, which is 1. So x minus 1 equals x squared. And then we have x squared minus x plus 1 equals 0. And then we're just solving that quadratic. Now nothing multiplies to make positive 1 and adds to make negative 1, so this is going to be a quadratic formula. So x is going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be positive 1 plus or minus the square root of negative 1 squared minus 4 times 1 all over 2 times 1. So x equals 1 plus or minus the square root of 1 minus 4 is negative 3 over 2. Now we can write this as 1 plus or minus I rad 3 over 2, but this is imaginary. This is a complex number. And again, if we go back to the original equation, our log base 7 of x can only take positive real numbers. So that means that we have no real solutions to this problem. Because logarithms don't take complex numbers. They're not actually quadratic, which means they don't actually have complex solutions. So our next example is going to be leaning more into the exponentials. So let's say we have 3 to the 1 plus x equals 17 to the 2x minus 1. So there are a lot of ways we can take this. My personal preference is to use natural log just because it's what I'm used to. So we take the natural log of both sides. 3 to the 1 plus x equals natural log of 17 to the 2x minus 1. And because of our logarithm properties, we can now take these exponents and bring them to the front. And we have 1 plus x times natural log of 3 equals 2x minus 1 times the natural log of 17. And then we're going to divide by ln 3. ln 3, we'll have 1 plus x equals 2x minus 1 times the natural log of 17 over the natural log of 3. And the only thing we can do now is actually distribute this whole thing to 2x minus 1. So we end up with 1 plus x equals 2x times ln 17 over ln 3 minus ln 17 over ln 3. And so this is being multiplied here. Then we're going to subtract over the x minus the 2x ln 17 over ln 3. And we're going to subtract the 1 this way. So I'm not going to rewrite this twice, but just know that I am subtracting it here and on the other side just like the 1. So we end up with x minus 2x times ln 17 over ln 3 equals negative 1 minus ln 17 over ln 3. I could factor out the x now. 1 minus 2 times ln 17 over ln 3 equals negative 1 minus ln 17 over ln 3. And then you just divide by this whole horrible binomial, ln 17 over ln 3. And we get x equals negative 1 minus ln 17 over ln 3 all over 1 minus 2 times ln 17 over ln 3. And there's no way to simplify this any further. The only thing we could do is use our change of base to write this as negative 1 minus log base 3 of 17 over 1 minus 2 log base 3 of 17. These two answers are the same. They're equivalent by our change of base formula. And if you had taken log base 3 of both sides to start, way up here, this is the answer you would come to. So some of you may take log base 3 or log base 10. Your answer may look different than this, but it will be equivalent. Now, if you do log base 10, you do the common log. Instead of ln's here, you'll just have log, 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 log. And if you do log base 3 of 17, you'll end up at this answer to start. But there's no difference between the two of them, and both of them are equally as correct. There's just more work involved, and it comes down to because our bases here are not the same base, we have 3 and we have 17, we can't rewrite them as the same thing. Okay, so let's try another one here. Let's look at, so that was a hard version with exponentials. Let's look at a hard version with logarithms. So this is D, or no, this is E. So ln x minus 3 square roots of ln x plus 2 equals 0. So the first thing we're going to do is rewrite this. Ln x minus 3 times ln x quantity to the 1/2 plus 2 equals 0. So a lot of students' first instinct is, oh, I can bring this 1/2 down, but we can't actually bring the 1/2 down because remember our logarithm laws say we're allowed to bring exponents of the argument of the x. So if this was ln x to the 1/2, we could bring the 1/2 in front. But since the 1/2 is being applied to the logarithm, it's not just being applied to the argument of the logarithm, we can't do anything with it. So what we can do is something that we did back in chapter 11, chapter 12. No, this is chapter 12, so it would have been 10 or 11. I can't remember. We're going to set u equal to ln x, and that makes ln x we're going to set u equal to ln x to the 1/2, and that makes ln x equal u squared. And then we get u squared minus 3u plus 2 equals 0. Now we're just solving a quadratic. And what multiplies to 2 and adds to negative 3? That's u minus 2 and u minus 3. Yeah, u minus 2 and u minus 1. That's how it works. This equals 0. So u equals 2 or u equals 1. And just as we did now, we're going to substitute back to what u is. So ln x to the 1/2 equals 2, or ln x to the 1/2 equals 1. So we're going to square both sides, and we get ln x equals 4, or ln x equals 1. And so ln x equals 4, remember this is, we can e both sides, or I say e both sides, but you're raising e to the power of both sides of your equation. E to the ln of x, this is the same as e to the log base e of x. And remember, anything raised to the log of the same base cancels, so this is x equals e to the 4th. And over here, if we e both sides, we get x equals e. Now this is greater than 0, and this is greater than 0. And that's important. Remember, x, since we have just ln x here, needs to be positive, strictly bigger than 0. Both of these are. E is 2.7 something, 2.17, something like that. E to the 4th is certainly bigger than that. So these become our final answers on this problem. So you can kind of see, even if we have exponentials and logarithms, we are able to solve it using quadratic methods, like we did in chapter 10. Chapter 10, I can't remember, 10 or 11. The last sections, the last couple chapters that we did with quadratics. And then we just have to make sure that they do work in our domain back in the original question we were given. And if they do, then great. So the last problem we're going to do in this section to finish out chapter 12, my paper, need more paper here. So the last section or problem we're going to do is a word problem. So we are going to let y equals y naught e to the 0.15t, where t is in months, represent the number of students who don't like math. We are going to use this model to estimate the number of students that don't like math in 6 months if 5,000 students currently claim to not like math. So this is what's called the exponential growth function. So this is, some people call it the shampoo formula because it's PERT, P-E to the RT. So a lot of times you'll see this as P naught e to the RT, and this is P of t, it stands for population. So P of t is population, E is just the exponential e. R is the growth rate. T is time. And P naught is the initial population size. I would box that up because that is not unique to this problem. This is a very, very common model. In fact, in light of our current situation during the coronavirus pandemic, this is one of the models. It's a simplistic model, but it's what a lot of the models that are tracking how fast the virus is spreading, how many new infections there will be. The model that they're using is built off of this relatively simple exponential model because viruses and bacteria reproduce at an exponential rate, meaning that they increase exponentially e to some power. So let's look at what we have. So we're using y naught e to the 0.15t. So instead of p, we have y. No big deal there. So our y naught, our initial, we look at our problem, that's how many right now, how many students don't like math right now? That's 5,000. So y naught is 5,000. Our r is already given to us at 0.15. Now, the rate is not always going to be given to you in the model like this. Sometimes they're going to say use an exponential model, or sometimes they'll say use this formula. And they'll tell you the rate is a percentage or a decimal. Now, the percentage for a 0.15 growth rate is 15%. So if they tell you a percentage, make sure you put it back in the decimal. So if we make this key up here, we change this to as a decimal. Because your growth rate needs to be a decimal to work in the formula. If you have your percentage, it's not going to work right. It's going to be too big. So that's our rate. Our t is in months. But the problem, I forgot this as well, is our formula should be always thought of in years. So we're going to need to convert to use this formula from months to years. So right now, we want t equals 6 months, which equals 1/2 a year. So we're going to have to convert that. And then we plug in our values. So y is going to equal 5,000 e to the 0.15 times 6 months, which is 1/2 a year. So this is 5,000 e to the 0.00, it's too many zeros actually. This is just 0.075. And so we're just plugging that into our calculator. And when we do that, we get approximately 5,389.42. Now, we're dealing with students, so you can't have 0.42 of a student, so we always round up when you're dealing with population size. And so we have 5,390 students that won't like math in half a year. Now, if you wonder why would that be? Well, if you figure we see about 1,000 students in math classes every semester, some of them already are counted in the ones that don't like math and they have to take multiple math classes, like some of you might be doing. This might be your final math class or your second to last math class. You don't like math, but you have to take it anyway. And some people take math because they think that they like it. And yes, people can like math. And then they take a math class, a hard one, and they realize they don't like it. So this actually makes sense. You know, if we see 1,000, maybe under 1,000 math students every semester, about 400 of them are going to come out a half a year later and realize, yeah, I don't really like math anymore. Or maybe they have a bad experience. Maybe this number shrinks from semester to semester. It's not really the point of the problem. The point of the problem is to determine how to use this type of model. And so this is the big thing. That's why I did it in black, because it is true all the time, not just for this situation. All right, so that is the end of section 12.8, and that is also the end of chapter 12. So the next couple videos will be about chapter 13. Our next test is on chapters 12 and 13. So keep a lookout for those.